Okay, it's 2 o'clock. Let's start the session. Let's start the show. Welcome, everyone. Good afternoon. Welcome, everyone, to the session on advanced networking. I know how it's difficult to come back to the sessions after a great lunch we just had, but I can promise you will be satisfied with excellent presentations we have today. We have 3 presentations. We will go deeper into some details of OpenFlow protocol. We also hear about the concept of network as a service. Last but not least, we'll also be given with a short explanation of what self-service networks are and what kind of services they offer to the eScience community. The first speaker today is Łukasz Ogrodowczyk. It's a colleague of mine from PSNC. He received the master's degree in 2007 from Poznań University of Technology. He joined the networking department in PSNC in 2010. He is involved in several European national projects. He represents here FP7 alien projects, which results is the main topic of his talk. Łukasz, welcome.
Okay. Thank you, Bartek, for kind introduction. Today I'm going to show you a presentation about hardware abstraction layer. We called it HAL for non-OpenFlow capable devices. And here is the agenda. First, I will try to answer the question, why do we need HAL? What is the HAL and how HAL is validated? Then I will show you architecture of the HAL as well as framework for the HAL implementation. And I will summarize my presentation with HAL advantages and future work related to hardware abstraction. So, networks are changing, and SDNs change the networks. SDNs offer new opportunities for control and management of the network. And hardware abstraction that sits between the hardware and software change the network devices into a programmable infrastructure. And the consequence of splitting the data and control plane is shifting the network intelligence from the hardware into the software into a central point to the SDN controller with global view of the whole network. And it's not melody of the future, it's something happening now. On the market, there are currently many OpenFlow switches which are designed to work with OpenFlow protocol. And that's okay, but what about devices that don't support OpenFlow? Don't support OpenFlow natively, like optical devices, like point-to-multipoint devices, programmable platforms, and others. What about legacy proprietary devices and even new hardware, but not natively OpenFlow enabled? Is it possible to add them under SDN control? That's a question. OpenFlow protocol was designed first to support Ethernet networks and doesn't support circuit switched, wireless network, point-to-multipoint modular systems. And the HAL is the solution. HAL concept allowed to add these devices under SDN control. What is HAL? HAL is a concept of first describing and exposing capabilities of network devices, and then to allow control the forwarding behavior into the hardware. It hides between SDN controller and network devices, and to make HAL as reusable as possible, we divided it into 2 sublayers, into hardware platform, cross-hardware platform layer, which is hardware agnostic part of the HAL, which is common for many devices, and hardware-specific layer, where we implement hardware drivers. HAL itself hides the complexity of network devices and vendor-specific features, and nowadays, they are ported to several platforms and can support SDN networks. And it is worth to mention also that HAL concept is known from operating systems like Linux or Android, where HAL enable access to the hardware through drivers which hide complexity of network devices and which implements specific features. And how HAL is validated. Currently, HAL works with different network devices, and we validate HAL using non-OpenFlow capable equipment. We call it alien devices because they are alien to the OpenFlow protocol. And HAL can control now the following set of platforms. Those are DOCSIS, is a known system from cable systems to our homes, GPON, multi-modular system, optical system, ADVA telecommunication system with KVM network processors, is also Easy Appliance programmable switch with EasyChip NP3 network processor, ATCA, Dell switch also with KVM network processor, NetFPGA cards, or even switches with standard CPUs like Intel Xeon. And for all these alien network devices, we try to design one common HAL architecture. The difficulties, we met some difficulties here because alien devices are very different and they differ in a way of control, way of management, way of forwarding. And we tried to gather common terms of these heterogeneous network devices and distinguish sublayer that would be common for many network devices and which provide common abstractions seen by SDN controller and OpenFlow protocol. Also, the big challenge was to deal with the issues of hardware openness to being programmed because many network devices are closed. They don't offer possibilities to data path to being programmed, or this access is limited. And here is the architecture. You can see that hardware abstraction layer sits between the control and management from the north, and just above network devices is split into two sublayers, into cross hardware platform layer and hardware specific layer with some functional components. And in the cross hardware platform layer, there is OpenFlow endpoint as well as virtualization component. In hardware specific layer, we have translation, orchestration, and discovery. And on the next slides, I'm going to describe it very briefly. So, OpenFlow endpoint establish channel connection to SDN controller. It is a parser of OpenFlow messages. It exchanges the messages to the controller and can be configured to support different OpenFlow versions. Currently, it's 1.0, 1.2, 1.3.2. There is also optional component, OpenFlow pipeline, which process packets abstractions instead of real network packets. It's a software realization of the pipeline. We have also a component called virtualization. It enables flow-based slicing amongst many controllers. It supports different versions of OpenFlow protocol. And virtualization agent is part of the plugin manager. It's an entity in cross-hardware platform layer. This entity gives the opportunity for easy HAL extensions through independent plugins. Example plugins are netconf or ofconfig, authorization, authentication, accounting. These plugins can stir the OpenFlow endpoint to speak with different controllers, even with different OpenFlow versions. Also, this plugin is capable of supporting other plugins modules, so could be easy extended. And hardware-specific layer, here we we implement hardware drivers. Discovery module is responsible for providing list of devices working together as a single platform. It provides information about interconnections between these devices. Also collects and then provides information about data plane ports with their characteristics. And there is an orchestrator module. Also, it's an optional module. It's used in case of multimodular systems like GPON and DOCSIS with head and tails. And it is responsible for sending the configuration to all registered hardware components and for keeping the consistency of the whole configuration. And the core of the driver is the translator. This module is responsible for translating the OpenFlow abstraction with flow tables, actions, port numbers into commands, processor instructions, or just part of configuration files through available interfaces, through APIs, through protocols that are available on the network devices below. And here on this slide, here's a framework for HAL implementation. It is based on ROFL XDPD, OpenFlow library, and DataPath daemon. It's a software framework for building OpenFlow DataPath elements. What is important here is that we have one common API, AFA. It's Abstract Forwarding API. It's software interface, C language-based interface that binds the hardware agnostic and hardware specific code. It's common for all these alien devices. You can also see that we divided alien devices into two groups, into closed box platforms with limited access to data path to being programmed, and programmable platforms with additional hardware pipeline API with access to softwareization of OpenFlow pipeline. And this framework is used into several platforms, also into eScience. We in PSNC deploy both sublayers of the HAL into host CPU board inside eScience. It's a Linux-based board, and HSL sublayer of the HAL support translation and discovery functionalities. We don't need orchestration in eScience because it's a standalone device. Network processor is accessed through EasyDriver library, proprietary library provided by EasyChip company. And in network processor unit, we implemented flow tables using memory structures. We also implemented from scratch the pipeline, OpenFlow pipeline, using assembler for task-optimized processors. The big advantage of the HAL architecture is the modularity. Thanks to this, HAL may be easy extended, easy modified. In case of new OpenFlow versions, in case of new versions of hardware, new versions of, or just a new hardware, just for adaptation of proper sublayer or proper component. And there is also a plugin manager for easy HAL extending for new features. HAL is now compatible with different heterogeneous network devices. And HAL is dedicated for both, for network operators. They may extend the OpenFlow-based network to new hardware, to legacy valuable devices. And is dedicated also for network equipment vendors, for HAL designers, HAL developers. They may reuse the code, which is open source code. And what is the future of the HAL? For sure, HAL is a key enabler towards network programmability. Now in PSNC, our research is focused on programmable abstraction of data path. It's very generic abstraction. We are not restricted there to OpenFlow abstraction and known protocol headers. We can define our own, and we can program the behavior of the network devices through generic bytes operations. And for sure, HAL may be used in all implementations of SDN concept where we split between data and control plane. I would like to also invite you to the Pioneer booth here at the Terrana conference. We prepared 2 demonstrations. First, about streaming on demand in OpenFlow networks. We present live working network devices, easy chip, network processors, and cards with Intel DPTK. During the second demonstration, we present DOCSIS platforms integration in Ophelia. It's a remote demonstration. Pioneer booth is number 17. And at the end, I would like to show you a few words, say a few words about ALIM FP7 project. It's an international project with 9 partners from EU, with PSNC as a project coordinator. It's a Firestrap project that will finish at the end of September this year. Here's also project website. That's all from my side. Thank you very much for your attention.
Thank you, Łukasz, for an excellent presentation. Any questions from the audience to the speaker?
What do you think of the Open Daylight project, and do you think part of your code could be a southbound plugin for Open Daylight?
That's a good question. I think yes, but Open Daylight is this solution, is the product which is ready to be used. Our HAL is rather for implementing OpenFlow into devices that don't support this protocol natively. But Plugin Manager offers for sure opportunity for adding new functionality. So any kind of interactions are possible, I think.
Any other questions to Łukasz? If not, thank you, Łukasz. Now we move to the next speaker, Dave Wilson from AGNet. There's an interesting story behind Dave and his presentation here. He was graduated from UCD in 1996. The funny story is that this room is used as a lecture room for computer science students. So he was sitting here 20 years ago. Now he's going to give an excellent talk on network as a service and open NAS. Dave, floor is yours.
Yes, it's very, very strange to be standing here. It's almost as strange as it was to sit there yesterday, which affected me more than I expected. But networks as a service. Last year in Maastricht, I stood here and I asked the question, what are routers for? And we got a couple of answers, but eventually it boiled up to the key is separation. They separate networks from each other, and that lets us manage them properly. And, sorry, this year I have a different question. Question is, what do networks do? What are they for? Anyone want to volunteer an answer? Transport. What's the purpose of transport? Lolcats. That's a great answer. I like that answer a lot. But what's the purpose of transport? Why would you transport things? That's a question, isn't it? What does it come down to? Sorry?
Collaboration.
Yes, I agree. It's, in our case, I think it's about connecting researchers to resources. It's our specific case, by the way. Thank you very much for those answers. Have a T-shirt. Hope it fits. And was it yourself? Lolcats, get your T-shirts. That's in our case, but it's not, that's a very specific case. It's not the generic case. The generic case I struggled with, and I think it's about, the best I could come up with was connecting devices to the internet. You know, I go through things like connecting researchers to resources, connecting people to networks, connecting devices to the internet. But then you get down to what is the internet. And I've been in so many flame wars that end in what is the internet, or they just go off the rails. And the best ending I ever saw was when on one mailing list, someone was going, yes, but what is the internet? And Seth Breitbart says, it's the largest equivalence class in the reflexive transitive symmetric closure, can be reached by an IP packet from. And at that point, it was dead, except for people asking if they could quote it. The problem is, I think you can't really get a good definition because IP networks, they're different for each user. Each user has a different use. But they all have very specific characteristics. There's things that IP networks do that other things don't. And there's things that are networks that are not IP networks. And these characteristics are now very well known. They're very well understood. And they're pretty ingrained in. Last week, I was at the RIPE meeting where we celebrated the 25th anniversary of RIPE. And it struck me that the network that we use and the technologies that we use, in many ways, haven't changed a lot in the last 2 decades. They look like this. These things are just so ingrained, at least in my mind, because I've been working with them for so long and it's how the network works, that we're just totally used to it. So what happens if you take some of these characteristics away? What happens if you break some of the rules? It's actually not as shocking as it sounds because we do this all the time. These things are all ways to take those characteristics and mess with them and to do something that you don't do on the normal IP network, and there's nothing really shocking about any of these. But these are manual changes. And the big deal about IP, and the reason some of us like me always go back to the IP network and how well the IP network works without making all these special changes, is that it scales so well. It scales, I mean, look at BGP. Can you imagine anything scaling like BGP? I still think it's a miracle it works, but it works. And it keeps on working. But that's the difference between the manual changes that we make and the automatic system that is the internet and the protocols that run on layer 3. Wouldn't it be great if we could change the rules of IP sometimes, but maintain that flexibility? And the thing is, this isn't really about technology. This is about what becomes feasible, operationally what becomes feasible when you take technology barriers away. Which is why I got mixed up in this stuff about networks, but specifically networks as a service. So what we mean by networks as a service in the JRA2 task in GN and GN3+, is we see it as a delivery model for services that are easy, either not so easy to deploy or not so easy to deploy efficiently right now. And this work, we started this work quite some time ago actually with the Manticore software, which is what you see in the video playing there. We created the Manticore project, which is FP7 funded. We created this tool called OpenNAS, and that tool, the development of it is now taken up by GN3+. And what we see is that you have the notion of infrastructure as a service, which everyone knows very well. It's you take infrastructure and you use virtualization to make it elastic and quick to provision. And we go, it should be possible to take networks and make them elastic and quick to provision and get all of the same advantages. And we use different things to do this. You need some sort of virtualized base layer, and that's what you're seeing there. In this case, we're manipulating logical routers on a couple of Junos routers. And we have these notions that we build into it. So you have to have some sort of a queue so that if something goes wrong, then the whole thing gets backed out if not. That's proof that I do have a logical router now called Charm, and another one called Strange. Freeman Dyson was here last night. Excellent lecture. So you need this virtualized base layer. You need a hardware abstraction layer, just like the last talk. It's necessary, and that's what glue we're adding here. And then you have these things you build on top of it. So you're going to need orchestration of cloud resources. So you're getting your network as a service and your infrastructure as a service, and that's the whole deal. That's the whole package. It needs to interwork with software-defined networking, of course. And the scope goes as far as including network functions virtualization. And that's where it gets really, really interesting for me, because if you scope out that far, then far be it for a command line tool that's just typing away and I'm making typos and recording every single one of them for posterity. But you get this idea of having an iPhone app that will provision all the resources in your network and all the resources that you need to make a network. I need a network with a DHCP server and a firewall and a web server and some other things. Please go and build that for me. Thank you very much. There we have proof that the two routers are actually connected together, because every demo here ends in a ping. And these are very busy areas of research in industry. And we see network as a service as the way to prototype these solutions and the way to provision these solutions. So the question is, how do they fit together? I'm throwing a lot of acronyms around here. How do they fit together? We came up with an analogy. And the analogy is the old controller view model setup. And we look at it like this. Instead of the controller, you have your architecture, your physical architecture. And this is definable by software. And you have separation of the data plane, the control plane, the service planes. They are built as you need them, as appropriate to the service that's being deployed. And that role is played by SDN. And then you have the view bubble, and that becomes the services which are exposed to the user. And you need to interface with the user as the user requires, which is not going to be, of course, the same interfaces as the individual components expose. And you have to provide, it's not just a matter of translating that, you have to delegate properly to the user, because, for example, an NREN needs to be able to deploy infrastructure and then delegate parts of that, but not all of it, to their users, who are the IT departments of the universities. And then they need to be able to delegate parts of that, but not all of it, to their users, which may be in academic departments. And that's the role we see for networks as a service. And then we have the bottom bubble there is resources and policies. I need a firewall, I need a DHCP server, something like that. I have a security policy I need to implement, and that's the role we see filled by network functions virtualization. And where it gets exciting is where these start to overlap, because they're not totally isolated, they're interworking with each other, and you get into some really cool and weird places where you have these virtualized programmable network infrastructures and the overlap between SDN and NFV, and apps turn up all over the place and things like that. But before we explode in a sea of acronyms, really what this comes back down to is resources. None of this that I've described is really particularly new. But when dealing with networks as a service, what really sold me on it was thinking about it in terms of seeing the network in terms of resources. The reason is this. I work for an NREN. I work for the one here. And our clients come to us with requests for, they come to us for network services. It's what we do, it's what we're good at. We deploy network services. And whenever we deploy a network service, that service has rules. It has some sort of definition. It has requirements it fulfills, and it has other requirements it doesn't fulfill. This is how we get things done. And our accuracy at predicting the precise requirements that customers will need now and in the future, it's tough. I mean, it's impossible to get it exactly right, and we keep trying to deal with that, because when you build something, people will find all sorts of interesting new ways to use it, and you can't predict those in advance. You can do your best. But we started this, and the first use case we picked was virtual CPE. I'm not going to get too deep into it, but it was an awesome first use case. It was a brilliant place to start, because everyone can get behind it. Everyone understands what it's for. Everyone understands what the CPE does. It's got this beautiful technical demarc. Everyone knows what the box is for. You have this wonderful use case for it, which is, or wonderful overt justification, which is, you have a box. It costs money, and it's consuming space and power and air conditioning. Let's take it away and make it a part of a virtual box. And everyone can get behind that, so it's so easy to justify. But it has a really cool undocumented feature. And the undocumented feature is, when you have it deployed, you're now on the campus network. these interesting services that are a whole part of what NAS can do are now very close to the users. It's a bit of a Trojan horse. Suddenly these are available to you if you want to take them up. The reason I get so interested in virtualization, though, and this is a big deal with software-defined networking, I didn't get SDN for a long time. I was seeing it, and I understood it intellectually, and I saw what it was doing. And OpenFlow is manipulating the forwarding table, so you no longer have a switch. You have, as Randy Bush called it, a forwarding engine, which is forwarding frames or packets based on something other than the MAC address. And that's quite cool, but I was just struggling to see the practical applications of it. I couldn't see how it affected me. I couldn't see how you'd run a network on these things. And at the last, at the right meeting, not just gone, but the one before that, I saw this wonderful talk, which I recommend to you, where some researchers, I think at Princeton, had implemented an internet exchange that was free from the limitations of BGP. I'd forgotten BGP had limitations. I've been working so long with how the internet works that I just thought this is how it is. I had molded the network to this. I had molded our users' expectations to this. And every now and again, someone would ask me to do something with the internet. And I'd go, sorry, it can't be done. Or it can be done, but only very badly. Because the tools at hand are very, very blunt. As we were hearing yesterday as well. The tools at hand are very blunt indeed. And then these guys come in and they're making an OpenFlow-based internet exchange. And I'm going, are you kidding? The fastest, the biggest, the most critical segments of the network, of the internet, are the internet exchanges, and you're introducing this technology on it. And they did it. And the result was amazing, because there were all sorts of drawbacks of the control plane that we have, where we have different ISPs trying to interact with each other, each with their own needs, and trying to find some sort of compromise in routing, which were constrained by the technology available. And then this takes those constraints away. And the sort of stuff they're able to do with it is fascinating. So I really recommend going, that talk is online. It's worth watching if you're in any doubt about SDN. And there's reason to be in doubt of SDN. There's a lot of hype. This one was dead solid and really very concrete. And, you know, okay, SDN's one way. We've been doing this kind of thing with VRS. We've been doing this kind of thing with MPLS for years. And it comes down to these two things. If you're going to introduce a service based on this stuff, we need a DMARC, and you need to abstract it properly. And our current ways of doing this, if we're going to deploy a service to a customer and try and manage it, like I was saying, we're really only of two ways. You can do something special, and you can do it manually, and you deploy it for that customer, and that takes time. And then the second customer comes along and they want the same thing, and it takes exactly the same amount of time, and you'll never scale that. Or you can automate it. And if you automate it, that's brilliant, and you get this infrastructure in place, and if someone wants a thing, they can have it in 2 minutes. Let's just type in your things, push button. Something went wrong, we'll just do it again, it's fine. But you're stuck with whatever templates you end up in there. And we were going, wouldn't it be great if you could get the advantages of both at the same time? So that's why we come around to resources. We see the network not as individual components, but as these things that you can manipulate, which can manipulate each other, and which interact with each other. And these resources themselves, these network elements have characteristics, or have functions, and they become characteristics of the resources. So I'm not thinking about a gig interface. I think about an interface, which has the speed of a gig and emits a certain kind of frame, fine. You can request a link. It may have to support VLANs. You can request a router, which itself might support virtual routers in it. And then the virtual routers themselves might not support virtual routers within those, or depending on the technology you're using. That's all very well. But you have these resources lying around the place, and they're some way implementing a physical infrastructure. How the hell do you put that together? And that's where the software comes in. We have this physical equipment at the bottom, and you have these services you're running at the top. And the green bit in the middle is your resources. And these are the useful things that we try to expose to someone who might want to use them. Not necessarily a user. The user's at the very top, but the resources themselves are exposed in some way that can interact with each other and with the layers in between. And what you get out of this is not a big complex diagram like that, but you pull out the bits you need to run the service you want. And that's what you're running. Which brings us all the way around to IP network overlays. At last, 15 minutes in, we get to the title of the talk. But I've already told you all about it. Because, as I've told you, we have these customers who need to run their own services subject to their own constraints. And if I, as a network operator, come in and say, I'm just going to add a couple of constraints, that's a big problem. If I go in and start changing the rules, they may conflict with their requirements. They may not be compatible with each other. And at best, they happen to coincide. Okay, we get lucky. And more frequently, they don't coincide so well, but we can find some way to hack it, and no one's really satisfied. And at worst, we don't have a customer. The customer walks away and goes to someone else who can serve their needs. And that's not actually a fact of life. That's not the way it has to be. Because remember the OpenFlow Internet Exchange, you can take those constraints away as long as you can find a way to manage it. So we do all this today manually. Or we do this today with a provisioning system based on templates, and it lets you do certain things well. We've been doing that with our point-to-point circuits for a decade, and it works so well. But the big deal with resources is, unlike a template, all these resources can interact arbitrarily. So the customer comes along and says, I need some things, please. I need to be able to do this. And I go, okay, that sounds like these components. Let me pull them out, and you tell me how you would like them to interact with each other. And they have the facility to do that. So where are we with this? Well, it does take work to get these layers in place. The resource layer is in there, and that's what you're seeing the video earlier. And now we're working on expansion expansion modules to be able to increase the reach of what this kind of thing can do. So there's a Quantum OpenStack plugin, there's a Bandwidth on Demand plugin, there's plugins for different types of routers, there's switches, there's ROADMs we can throw in there if you want, it's OpenFlow switches. There's various extensions to configure different protocols. So we started with things like OSPF and BGP early to get the first use cases in, and then work out from that. If you'd like to see more about that, I2CAT are demonstrating this in their booth downstairs. As you go back out, it's on the right at the corner, and they'll be delighted to show you. And then over the next 6 months, we have more use cases to integrate, and we're going to be continuing to work on that. So that brings me back around to this business of the end of history illusion, which sounds quite apocalyptic. It's a lot less apocalyptic than it sounds. The end of history illusion is the idea that, and as human beings, we're all sort of subject to this, we sort of assume that the future is going to be roughly as it is now, with a few changes. And it's patently not the case, because we can see over the years and over the centuries, there are big changes, there are disruptions and there are revolutions now and again. But you can't predict that sort of thing. So as human beings, what the mind does is it goes, well, I guess in the future it's going to be more or less what we have now with some differences, because no other answer makes sense. It's no more plausible. It's a bit like saying the lottery numbers can never be 1, 2, 3, 4, 5, and 6, even though they can, and it's just as unlikely as you actually having the winning ticket. It's a bit like that. And I felt a bit like that with IP networks, because it feels like a lot of the innovation has gone out of IP networks, and it's gone to other layers, and it's gone elsewhere, higher or lower. All the improvements that we see feel sort of incremental. They're kind of small. There's been changes over the past 20 years, but they feel sort of, okay, they're a little bit obvious in hindsight. And individually, they're all kind of what we call sustaining innovations. And I'll be talking about more about that in the next room in the next session. But basically it comes down to things like we had the phone network, and that was great, and then we had fax, and that was sort of an incremental improvement on the phone. We can send pictures over the phone, whoopee. And it wasn't until we got these our own endpoints, we could start deploying our own endpoints on the phone network, that things got really interesting again. That's when we got IP. Now it feels like IP got boring again, and we've been sort of commoditized. Years ago, I used to use this as my signature in emails. Steve Deering saying, IP is difficult to charge for. That's not a bug, that's a feature. And now I think we've come around again, because IP is this commodity. It's so well understood. It's so ingrained. We can't really change very much in case it disrupts something. But network as a service is this tool that we're building, which is trying to change that, but it's grounded in our community and it's grounded in the needs of our community. And this matters to you as NRENs and as users of NRENs, because this is our big advantage over the commercial world. It's difficult to see sometimes unlike 20 years ago, what the purpose of an NREN is sometimes. And this is where we're at our best, because we as NRENs, as these strange non-profit entities that like to cooperate and do research, we have the freedom to expose our resources quite smoothly. And we have to get it technically right, and we have to get it operationally right, but business-wise, it works pretty well. We can get on with each other and do this. And we can interoperate in a way that commercial networks find very difficult to do. And that means that we can take the very best of what each NREN does and present that entire package to all of our customers. And that sort of combination is absolutely unbeatable. But it only works if we're implementing, if the tools we're using are implementing what we actually need. And that's why there's an open as users mailing list here that I'd love you to come and subscribe to download the software, try it out, and tell us what it is that you need. Thank you very much.
Great talk. Thank you, Dave. I'm not sure how many T-shirts do you have, but I encourage you to ask. So I encourage you to ask questions. There are some prizes.
Nope, not for one more T-shirt?
Just one T-shirt to go.
If you're curious, as I said, the Articat guys are downstairs in the booth. There's also a few other members of the project who are here, sitting there, and I'm sure I'd be delighted to talk to you afterwards as well.
Okay, thank you very much for your talk. And now we go. Now we move to the last speaker in this session, Ronald Waldenpol. He has been working for more than 20 years in research and education community. Since 2012, he's working on network innovation projects at SurfNet. Previously involved in research work in University of Amsterdam, SurfNet, NLED Labs, and SARA.
Okay.
Please.
Yeah. Thank you for the introduction. So my talk is about the community connection service for eScience. This is a Gen 3 Plus open call. It started in October last year and it runs until March next year. Partners are two partners, SurfNet together with TNO. The budget is 216,000 euros and we split this between the two companies. There's 16 person months involved and we also split that evenly. And we have defined 5 work packages. First work package is defining the use case and requirements, the market demand. Second work package is about the architecture, defining the architecture, implementation, design and development. Third one is about experimental validation, testing what we have built and designed. And then fourth work package is about dissemination, as I'm doing right now. And the fifth package is the usual project management. So what is the goal of the Community Connection Service, COCO for short? It's an on-demand virtual private multi-domain multi-point layer 2, layer 3 network instances. So what does this mean? On-demand means there is no human interaction involved. It's automated. Virtual, like the previous talk, it's virtual networks. Multi-domain, so over multi-domain, not just running on SurfNet, but over multiple domains. Multi-point, we have a couple of inter-domain point-to-point services these days, bandwidth on demand and things like that. We extended to multi-point services. And we want to have a layer 3 VPN and layer 2 and layer 3 VPN service on top of that. The intention is to interconnect eScience resources like laptops, virtual machines, storage, instruments, etc. And the idea is that eScience communities, virtual groups, closed communities, can set up such virtual networks themselves and then have a network between them. They can do this by using a simple-to-use web portal. And in this project, we are going to build that on top of an OpenFlow infrastructure. So this is an example. It's a couple of domains, SurfNet, Jant network, other network, another NRN, interconnected via Jant or via goals, and a couple of customers. These 4 customers want to interconnect their resources over a virtual private network, and that's shown over here. And you can have multiple of these instances at the same time. That's the idea of the project. So we started with the requirements, the use cases. We held a workshop in the beginning of the year at SurfNet in Utrecht, the Netherlands. We invited Dutch eScience researchers. There were about 15 participants. And we had a goal for this workshop that was twofold. On one hand, we wanted from this community, we wanted to hear what their requirements were and use cases for such a service. And the other goal was from those participants, get people involved that want to act as potential test users. So the results from the workshop came out a couple of service requirements, more than we can accomplish in the prototype we are building, so we have to make choices. We can't do all the requirements. And there's two most interesting use cases. One of them is shared electron microscope, so an electron microscope connected to a server, and that server can be eScience biologists, etc., can connect to that server and work on that electron microscope. And the other one is DNA sequencing. The next steps after this workshop are to refine those 2 use cases. And also to get in contact with the network administrators, because what bandwidth on demand services, point-to-point services, LightPass showed that you really need to involve the network managers if you are going to bring a service into the campuses, as this is also doing. And we also have to better define the authentication and confidentiality. Sometimes the data can only be shown by part of such a community, things like that. So after that, the last few months, we have worked on the architecture. This is an example as we are thinking about at the moment. At the bottom is the data plane, and on top is the control plane. So data plane, control plane separation. These is just the forwarding of the data through the network. The dark gray areas are different domains. So this is inter-domain. And in each domain there's a couple of OpenFlow switches in our case. And there's a centralized controller for those switches, and we call that the COCO agent. So that's more than just an OpenFlow controller, it's the whole infrastructure needed to run this service. So the domains are interconnected. There's a couple of customers. Each domain runs its own Cocoa agent. Each domain runs a web portal. That web portal is used by the eScience researchers to pick the sites where a VPN needs to be, between which a VPN needs to be configured. Yeah, that's basically the broad overview of what the architecture looks like. So the Cocoa control plane, the top layer, it consists, as I said, each domain runs its own Cocoa agent, and they are working together in a federated way. The Cocoa agents will be built using Open Daylight. That's has become such a popular project that we decided to use Open Daylight, not only for this project but also for other projects. And then these Cocoa agents that each domain runs need to exchange information with other domains via some kind of east-west protocol. We are now thinking about using a BGP-like protocol for that. And that information that needs to be exchanged is about the end nodes, which end nodes are available as end sites for the Cocoa servers, so that they can be shown on the web portal, and the users can pick sites out of that list. There's multiple Cocoa instances running on the infrastructure, so you also need to exchange information about identifiers of particular Cocoa instances. We are going to use MPLS-based forwarding, so information about MPLS labels needs to be exchanged between the domains. Addresses, of course, needs to be exchanged, either layer 2 or layer 3 addresses. And authentication groups, etc., policy needs also be exchanged between the agents. And finally, what the Cocoa agent does is, of course, configure the forwarding entries in the control plane in the OpenFlow switches. And that's done via a southbound interface, the OpenFlow protocol. So the forwarding plane, the data plane, as I said, it will be MPLS-based. We'll use two MPLS labels, an outer label and an inner label. The outer label will be used to identify the provider edge switch and forward to that provider edge switch. And there's an inner MPLS label that identifies the Cocoa instance. We will do shortest path forwarding towards provider edge switches, and probably a primary and a backup path for redundancy. At the edges there will be encapsulation and decapsulation at the provider edge. And customer traffic will be encapsulated with an MPLS label at the edges. And then in a core will be forwarded based on that MPLS label. So in the core, all the traffic is aggregated so that the forwarding entries in the core are kept to a minimal. This is how it looks like. Customer side connected to a provider edge switch. Here another customer connected to a provider edge switch. Traffic of this customer, suppose this customer C1 wants to talk to C3. Traffic destined for C3 is encapsulated here with an MPLS label that belongs to this provider edge. And in the core, in all those switches, forwarding is just done on that MPLS label. Ends up here Here it is decapsulated and sent to the other side. So we have defined two ways in which customers can connect to the service. One of them is via a VPN client, for example, OpenVPN. That's shown over here. So this is a customer. He installs an OpenVPN client on his laptop and then connects to a VPN server running in the domain. Each domain can run its own VPN server. So you connect to the VPN server of your own NRN. The typical use cases for those are laptops, users with laptops. And the second connection model is based on installing an OpenFlow switch at the site. And this is used for connecting servers, instruments, etc. And then the campus network administrator gets involved. He installs that OpenFlow switch. What he also needs to do is, of course, connect all the resources, the servers, instruments, etc. And he configures one dedicated VLAN on the campus infrastructure, and that is dedicated for the COCO servers. So all COCO-like traffic is sent within the campus over that VLAN. We choose this because that VLANs are supported on most campuses, and configuring one additional VLAN isn't that hard, we think. So we think this is a feasible way of introducing the service in campuses. And then what also needs to be done is that domain also needs to run on top of that OpenFlow switch a COCO agent, a stub COCO agent we call it. And that peers with the COCO agent of the NRN, of which the customer is, of this site is a customer of. So this is how this looks like. At the right is the provider, the NRN with its own COCO agent. This is the campus network, a normal edge device that just needs to forward the traffic from that VLAN. That VLAN is COCO VLAN is configured in the campus, and that traffic ends up here and is sent to the provider. And the OpenFlow switches connect the COCO resources, servers, etc. Runs a COCO agent, and there's a peering relation between the two agents. So at the edge, there's encapsulation and decapsulation at the provider edge. And layer 2, layer 3 addresses are encapsulated there with an MPLS label. For layer 3 addresses, we use IPv4, IPv6 prefixes. That's the easy part, we think, because those are aggregatable and thus scalable. But we also want to investigate layer 2 addresses, so layer 2 VPN servers. And those are, of course, more difficult because layer 2 addresses, MAC addresses, are a flat address space. So you can't aggregate those, and special attention is needed there. And I have an additional slide on that later on. So first, the layer 3 VPN servers. In that case, each site has its own IPv4, IPv6 prefix. The address assignment is done at the site itself. Normal case. DHCP, DHCP-v6, auto-configuration, etc. And this is all proven technology. It's just like how the internet works. There's one thing that is different from just the internet is that the infrastructure is based on OpenFlow switches. And in OpenFlow switches, they just forward frames. They don't normally do MAC rewrite on each hop as a router does. So what we need to take care of is when a packet enters, when a packet exits the COCO network and is sent to a server or a router, a traditional IP device, that frame gets the right destination MAC address. Otherwise it is dropped by the interface. So we can do that either at ingress. At ingress already set the proper destination MAC address of the final destination, or at the last hop we do a rewrite. And this is possible because we are using OpenFlow with centralized intelligence, so we know these MAC and IP addresses at the edges. Layer 2 VPN service is more difficult. As I said, the MAC addresses are a flat user space. There's three challenges for that. MAC learning at the edges, how do you do address assignment, and what do you do with broadcast, unknown unicast, and multicast traffic. So the three challenges: MAC learning. You do need to do MAC learning at the edges. At the edges you need to know which layer 2 addresses are situated at which site, so that you know to which provider edge you need to send the traffic. There's existing technology and evolving technology for that. In Trail there's the eScience protocol that takes care of that. And the Trail working group in the ITF is also defining a directory-based mechanism for having a list of layer 2 addresses and where they are in the topology. And there's also another protocol defined standardized by the ITF. That's eVPN. And that uses multi-protocol BGP and an address family inside that. And in that, using that, you can exchange not only IP addresses with BGP, but also layer 2 addresses with BGP. And then, of course, there's the question at the edges: do you insert forwarding entries for all MAC addresses used in the instance, or do you insert only the active addresses and do you let them time out? What, of course, makes the forwarding table smaller. But then the disadvantage is if it is timed out, you need to reinsert it when a new packet arrives. Second thing is address assignment. It's each COCO instance, in that case in a layer 2 VPN service, is one layer 2 network, so one IP subnet. And you need to make sure that the MAC addresses and also the IP addresses are unique within a COCO instance. You also need to make sure that MAC addresses are unique, because in cloud environments, MAC addresses are usually generated by the cloud software, and you need to make sure that there are no clashes from a cloud inside one customer and a cloud inside another customer. So what you need to do, either a centralized sort of database, or you need to exchange information about layer 2 addresses, which addresses are free, so that you don't get clashes. And finally, the broadcast, unknown and multicast traffic. There's also two choices: either implement multicast in that network, like VPLS does, but that can generate a lot of traffic. Internet exchanges have problems with that, especially ARP traffic. Or what you can do is forward that BAM traffic to the controller and let it handle by the controller. And then the controller can do proxy ARP. And then the question is, are you going to do that for all traffic, or do you still multicast? Do we still implement a multicast service and run other less chatty protocols over a multicast data plane? So, in summary, the objectives we have with this project seem to be welcomed, or are welcomed by the participants of the workshop. It's a prototype, so we can't do all the requirements. We'll make it scalable by using MPLS in the core, and encapsulation, decapsulation at the edges. It's multi-domain, so you need to exchange information between the domains. And we are thinking about the BGP model for doing that. That's existing technology that already takes care of loops in the infrastructure, for example. Scalability is easy for layer 3. It's similar to internet. For layer 2 scalability, that's much harder. So we will also start with a layer 3 service, and if time allows, we'll go to layer 2 service also. So what are the next steps? We are now going to implement this, as I said, on top of based partly on top of Open Daylight and inside Open Daylight. With a single domain, we start with a single domain, the SurfNet OpenFlow testbed, and later we are going to extend it to multi-domain using the Jant OpenFlow testbed. We also have started on the test plan for testing the servers, and we need to involve the network managers. And then probably somewhere at the end of the year also have a follow-up workshop with the end users. There's some related work. I already mentioned VPLS, much used in internet exchanges. It's eVPN that's now being standardized and implemented. Cisco, Juniper support that in some releases. And there is the BGP, MPLS, VPN based stuff, and that is, for example, used in the Jant MDVPN service. And thank you for your attention.
Now, Ronald is waiting for your questions. There is one question over there.
Good morning, good afternoon, Ronald. Thank you for your talk. Can I ask you a question related to the slide number 12? In your project, is it required that the MPLS layer is connected to a Coco agent, or can it work simply with the OpenFlow controller on the stub Coco agent and nothing between there? And does the Coco agent work right now?
I don't think I understand your question completely. I think you said, is the MPLS label going to the Coco agent?
Yeah, the point is to know if the forwarding all the things that it is between two domains is simply handled completely by MPLS layer, and Coco doesn't provide any signaling or any controlling on this, or is it required to have this Coco agent that the Coco agent is only used to decapsulate the packet?
Okay, yeah, I think I understand your question now. I think your question is related to, is it all OpenFlow switches, or does this interoperate with parts that are just MPLS forwarding? Yeah. At the moment, we assume that they are all OpenFlow agents, so they are all controlled centrally by a COCO agent. So there's no signaling MPLS label setup signaling or LSP signaling to traditional MPLS domains. Maybe it's probably a next step, because you see this looks very much like MDVPN, and we thought about interoperability with that, but it's only an 18-month project.
Okay, any other question? If not, before I close the session, I got an email from Jonji asking for some announcement. So I would like to remind you about voting for your favorite student poster. So please vote for the best TNC2014 student poster. Place the sticker under, which is in your badge, on the votes paper. Feedback is very important, so please provide feedback. Please use the online version or the application. Extra events. There are booths and workshops this evening, so make the most of TNC to join them. There are still gala dinner tickets available at the registration desks. Shuttle buses for gala dinner are announced today via email, so you should have received them. If there are any questions, please check with the registration information desk. And last but not least, tickets are available for Thursday airport shuttle. A cheap bus, €10, from the TNC venue to Dublin Airport will be available on Thursday for anyone reserving and paying in advance in the registration desk. So if you plan your trip on Thursday, please book your shuttle in advance. I would like to say thank you to all speakers and to all of you for the participation in the session. The session is closed. Thank you.